You know, when you hold a single uncracked egg in your hand, it feels like this perfect, simple object.
Yeah, it really does.
It's like a smooth white stone, comforting, familiar, and you crack it into a pan, and you are looking at a true nutritional powerhouse.
Absolutely. I mean, for a lot of people listening right now, it is one of the most efficient, affordable sources of high-quality protein on the planet.
Right. But wrapped up inside that perfect yellow yolk is a massive, incredibly complex scientific controversy
Without a doubt.
because that tiny vault also holds a pretty hefty dose of cholesterol.
It really is the ultimate nutritional paradox. You have this vital global food source, right?
Yeah.
Something that has sustained human populations for literally thousands of years.
Yeah.
But for decades, it has been at the absolute center of debates about human cardiovascular health. It's a cheap superfood, but it comes with a catch.
And that catch is exactly what we are diving into today. So for this deep dive, we are looking at a really comprehensive 2026 scientific review.
From the journal Tropical Animal Health and Production, yeah.
Exactly. It's titled Strategies to Reduce Cholesterol Content in Poultry Eggs, an overview. And our mission today is to explore the cutting-edge, frankly mind-bending science behind transforming the ordinary egg into a low-cholesterol designer egg.
Which is just a wild concept.
It is. We are going to journey from the wild dietary hacks used by farmers all the way down to the microscopic world of gene editing and nanotechnology.
All to find out how scientists are trying to build a better breakfast for you.
Okay, let's unpack this. Why are we still so worried about the cholesterol in an egg? I mean, haven't we kind of moved past the eggs are bad for you phase of the 90s?
We have, yeah, in a general sense. But we really need to look at the raw numbers first to understand the lingering concern here.
Okay, hit me with the numbers.
So a single average-sized egg packs about 163 to 165 milligrams of cholesterol.
That sounds like a lot for something so small.
It is. If you isolate just the yolk, you're talking about 500 to 1900 milligrams per 100 grams of yolk.
What?
Yeah, in the landscape of human food, that is incredibly cholesterol dense. Now, you are right about the shifting narrative, though. The broader link between dietary cholesterol, meaning the cholesterol you physically eat, and cardiovascular disease is fiercely debated right now.
Right, because my understanding is that the cholesterol in your blood is mostly manufactured by your own body, right?
Yes, exactly.
Often in response to like saturated and trans fats rather than just directly absorbing the exact cholesterol you ate for breakfast.
Ah,
So saturated fat is usually deemed the bigger culprit.
that is the consensus for the average person, yes. But, and this is a massive but that the review highlights, we have to account for genetic variability in humans.
Okay.
This is where the push for a designer egg becomes deeply relevant. What's fascinating here is the phenomenon of genetic hyperresponders.
Hyper responders. Okay, that sounds like a comic book origin story. What does that actually mean for someone listening?
Right. So it means that while the average person's body regulates its own cholesterol production pretty well regardless of what they eat, a hyperresponder's body does not.
Oh, I see.
These are individuals whose blood cholesterol levels spike significantly and dangerously after consuming dietary cholesterol, like what you find in eggs.
So if I'm a hypo-responder, eating a 3-egg omelet barely moves the needle on my blood work.
Exactly. But if you are a hyperresponder, or say someone dealing with type 2 diabetes and existing metabolic vulnerabilities, absorbing that 165 milligrams from a single egg is a genuine public health concern.
So for a significant chunk of the population, eggs really are a roll of the dice.
They are, and that is what makes the quest for a designer, low-cholesterol egg a true public health need.
It's not just some luxury health food trend.
No, not at all. It's about preserving a cheap, vital protein source for vulnerable populations globally.
Which brings us to the factory itself. Because before we can even talk about taking the cholesterol out of the egg, we really need to understand how it gets in there in the first place.
It's quite the process.
I mean, how does a hen actually pack all that cholesterol into that tiny yolk?
It is an incredibly tightly regulated biological assembly line, and it moves fast.
How fast?
The whole process of making an egg takes about 24 to 26 hours.
Wow, that is fast.
Yeah. The entire operation is governed by something called the HPG axis, the hypothalamic pituitary gonadal axis.
Whoa, okay, let's pause right there. Hypothalamic pituitary gonadal axis. To anyone without a biology degree, that just sounds like alphabet soup.
Fair enough, I get that.
How does that translate to the hen's daily routine?
Think of the HPG axis as the factory's executive management team. It all starts with environmental cues, primarily light.
Like the sun coming up.
Exactly. When the sun comes up or the coop lights turn on, it triggers the hen's hypothalamus, the boss in the brain.
Okay, the boss is awake.
Right. The boss sends a chemical memo to the pituitary gland, the middle manager, which then sends hormones down to the workers, the liver and the ovaries. This kicks off the 24-hour manufacturing cycle.
So the liver and the ovaries are doing the heavy lifting, but where does the cholesterol actually come from? Do they just eat it?
No, in birds, the liver is the primary manufacturing plant for cholesterol. It uses a specific chemical pathway called the HMG-CoA reductase pathway to build the cholesterol molecules entirely from scratch.
Incredible.
But building the cholesterol is only half the battle. The liver then has to ship it to the ovary to get it into the developing egg yolk.
Okay, so how does it travel?
This is where estrogen steps in, and its role is vital.
Wait, estrogen, like the hormone, what does estrogen have to do with shipping cholesterol?
Estrogen acts like the logistics manager. See, cholesterol is a fat, and blood is mostly water.
And fats and water don't mix.
Precisely. So estrogen modifies special carrier proteins to create what we call VLDLA. That stands for very low-density lipoproteins, along with another crucial protein called vitellogenin.
Okay, VLDLE and vitellogenin.
Right. Estrogen essentially packages the raw cholesterol into these specialized water-soluble containers so they can safely travel through the bloodstream.
So it's like a highly secure delivery service. The liver is the packaging plant, boxing up the cholesterol into these specialized VLDLE parcels.
Yes, I love that analogy.
And then they travel through the bloodstream to the ovary, and only the developing egg has the specific key, the LR8 receptor, to sign for the package and let it inside.
That is a perfect way to visualize it, because these VLDLE particles are specifically modified by estrogen to be extremely tough.
Like armored trucks.
Exactly. They are designed to resist being broken down by other organs while they are in the bloodstream. They truly are armored trucks driving straight to the oocyte or the developing egg cell.
And the egg cell is just waiting there.
Right. The oocyte cannot manufacture its own yolk components. It absolutely relies on its LR8 receptor to act as the loading dock, catching those VLDLE armored trucks and pulling them inside the egg.
That is wild to picture. The hen is basically running this relentless 24-hour, highly secure cholesterol shipping network.
Day in and day out.
But does this network ever change? Like if I have a young hen just starting out versus an older hen who's been laying for a couple of years, is the egg different?
It is, and it's a very counterintuitive quirk of biology, actually.
Oh, really? How so?
As hens age, their reproductive machinery slows down slightly, and they naturally lay larger eggs with heavier yolks.
Okay, makes sense.
Now, because the physical egg is bigger, the total amount of cholesterol inside that egg actually goes up.
Right. Bigger egg, more room, more stuff inside it.
Right. But because the actual volume of the yolk increases so disproportionately, the concentration of cholesterol, meaning the milligrams of cholesterol per gram of yolk, actually goes down.
Oh, I see. It's like adding a shot of espresso to a small cup of milk versus a massive bucket of milk.
Yeah, that's exactly it.
The total caffeine is the same, but the concentration is heavily diluted in the bucket.
Precisely. The cholesterol gets diluted as the hen ages, and on top of age, genetic background plays a huge role. Different breeds of chickens naturally have different baseline settings for how active those liver enzymes are or how many LR8 receptors the egg has.
Okay, so now that we know the liver is the packaging plant and we understand the armored truck delivery routes, the big question is, how do we slow down production? If I'm a farmer trying to make a low cholesterol egg, the most obvious, accessible intervention seems to be just changing what the hen eats, right?
That has been the traditional approach, yes.
And going through the research review you brought, some of the things scientists are feeding these chickens are just wild.
The variety of feed additives they have tested over the years is truly staggering.
I mean, I'm reading this list, and we're talking garlic powder, shiitake mushrooms, microalgae, fish oil. I even saw fermented pineapple peel waste and pumpkin seed meal.
It is quite the menu.
It sounds like these hens are dining at a high-end, farm-to-table organic cafe. How does feeding a chicken something like garlic actually stop cholesterol from getting into the egg?
It all comes down to the specific bioactive compounds hidden inside those foods and how those compounds throw a wrench into the hen's internal factory.
Okay, give me an example.
Let's look at their strategies. Strategy number one is literally trying to break the assembly line. Let's take garlic, as you mentioned. Garlic contains a powerful, volatile organic compound called allicin.
Allicin, that's the stuff that gives garlic its strong smell.
Right. Exactly.
Right.
When the hen digests allicin, it enters the bloodstream and travels to the liver. There, it actively inhibits specific liver enzymes. Most notably, it suppresses an enzyme called squalene monoxygenase.
Okay, there's the alphabet soup again. Squalene
I think so.
monoxygenase.
Hmm.
If the liver is the factory, what is that enzyme's job?
Think of that enzyme as a highly specialized worker on the assembly line whose only job is to weld two critical pieces of the cholesterol molecule together.
Okay.
If Allison from the garlic comes in and taps that worker on the shoulder and says, "Take a break," the assembly line halts. The liver simply cannot manufacture as much cholesterol because that specific step is blocked.
That's incredible. So the garlic is basically a targeted strike on the factory workers.
Pretty much.
What about the shiitake mushrooms? That one really threw me.
Shiitake mushrooms use a different strategy. They contain a specific alkaloid called aritidenine.
Iridoxine.
Right. This compound targets a completely different part of the liver's process. It inhibits an enzyme known as PEMT, which handles hepatic phospholipid metabolism.
Hepatic phospholipid metabolism. Let's translate that for us non-scientists.
Okay, think of phospholipids as the specialized packing materials needed to safely load the cholesterol into the armored trucks.
Oh, like bubble wrap.
Yeah, exactly like bubble wrap.
Yeah.
PEMT is the shipping supervisor in charge of that packing material. By feeding the hen shiitake mushrooms, the aritidenine distracts that shipping supervisor.
So the bubble wrap doesn't get used properly?
Right. It alters how the liver handles those packing materials, which indirectly suppresses the synthesis of cholesterol and keeps it from getting incorporated into the yolk.
So garlic stops the assembly line, mushrooms mess with the shipping supervisor. I also noticed fish oil and microalgae were huge focus areas in the research. What's their strategy?
Rerouting materials. Fish oil and microalgae are packed with DHA, a long-chain omega-3 fatty acid.
Right, we hear about DHA a lot in human supplements.
Exactly. When a hen consumes high levels of DHA, it induces the expression of something called acyl-CoA synthetase. In plain English, it dramatically lowers the amount of raw triglycerides and cholesterol floating around in the blood.
Oh, I see.
If there are fewer raw materials available in the bloodstream, there's less for the liver to pack into those VLDL armored trucks heading to the ovary.
Even vitamins and minerals seem to get in on the action. I was reading about selenium.
Yes, selenium acts more like a management memo from the top down.
How so?
Supplementing a hen's diet with selenium increases a specific compound in the bird's body called 15-DPGJ2. This compound acts like a drug called troglydzone, which ultimately regulates a master protein known as SREBP2.
SREBP2. Okay.
SREBP2 is essentially the dial that controls the entire factory's output. By feeding the hen selenium, you are sending a memo to that master dial, telling it to turn down total cholesterol production.
Okay, wait a second. I have to push back here because this all sounds incredibly neat and tidy on paper.
Oh, I know where this is going.
If we're just tossing garlic powder, mushrooms, and fish oil into their feed, are we actually stopping the biological assembly line at the source? Or are we just, say, giving the hen a stomach ache so she eats less?
That's a very fair point.
Or maybe the feed just makes them lay smaller eggs, so there's less cholesterol by default because the egg is tiny.
That is a brilliant question, and you've just hit the nail on the head regarding the major limitation of current nutritional science in this field. Most of these feed additives reduce egg cholesterol indirectly.
Indirectly, meaning we aren't actually rewriting the factory rules, we're just messing with the building.
Precisely. A lot of these diets might simply interfere with intestinal absorption, meaning the hen just absorbs less fat from her food overall because the fiber content is too high.
Right.
Or, as you suggested, they might just alter the egg size. Very few of these simple dietary hacks are proven to directly suppress the liver's underlying cholesterol biosynthesis at a fundamental genetic level without causing other side effects.
And I imagine because it's indirect, the results are all over the place?
They are wildly inconsistent. One farm feeds their flock garlic and sees a 20% drop in yolk cholesterol. Another farm tries the exact same garlic powder and sees absolutely zero change.
Because there are just too many variables.
Exactly.
The breed of the chicken, their age, the temperature of the coop, how much they actually felt like eating that day. It sounds exhausting for a farmer to try and manage.
It's a very imprecise science right now. The hen's body naturally fights back to maintain homeostasis. If you block one pathway with diet, the liver often just finds a workaround to keep pumping out cholesterol.
Well, here's where it gets really interesting. Because if diet is an unreliable, indirect hack, scientists aren't just throwing their hands up and stopping there.
No, they certainly aren't.
They are taking a much more radical approach. To fix the factory permanently, we have to go deeper than the stomach. We have to look at the DNA.
Yes. We are officially entering the era of omics technologies in agriculture.
Omics, break that down for us. What does that actually mean?
Omics is an umbrella term for biological sciences that end in omics. It includes genomics, which is the study of the entire genetic code,
Okay.
transcriptomics, which looks at how those genes are actually expressed in real time, proteomics, the study of the proteins being built, and lipidomics, analyzing the cellular fats.
So instead of feeding a mushroom and just crossing our fingers and guessing what it does to the liver, omics allows scientists to see exactly what is happening.
Exactly. It's like going from watching the factory from the outside with a pair of binoculars
Hmm.
to hacking into their internal security cameras and watching every single machine operate.
Wow.
Omics allows researchers to see exactly which genes and proteins are turning on and off in real time when a hen eats something.
So it's high-definition biological surveillance. What are they finding when they zoom in that far?
They are finding incredible, actionable breakthroughs. For example, researchers used omics to study what happens when you feed hens a specific extract called alfalfa-saponin.
Alfalfa saponin.
Right. They didn't just guess, they tracked the genetic response. They found that this extract doesn't just block cholesterol creation. It actively upregulates an enzyme called cholesterol 7 alpha hydroxylase in the liver.
Upregulates, meaning it turns the volume knob up on that enzyme.
Right, it cranks up its activity. And the specific job of this enzyme is to increase cholesterol catabolism.
Catabolism meaning breakdown.
Yes, it acts like a garbage disposal. So the alfalfa extract actively forces the liver to break down and eliminate cholesterol rather than shipping it to the egg.
That's amazing.
But the science gets even more futuristic than that when we look at microRNA technology.
MicroRNA. These are the tiny molecules in our bodies that regulate whether a gene is turned on or off, right?
Correct. They are the chemical switches.
Mm.
Researchers have isolated a specific microRNA in chickens called miR34A.
Okay.
Using advanced techniques, when they overexpress this, meaning they flip this switch to the on position in a hen's liver, it actively inhibits an enzyme called ACSL1. By doing this, they negatively regulate the liver's lipid content at a fundamental genetic level.
So they are literally hitting the mute button on the genes that allow cholesterol to accumulate.
Yes. And some scientists want to go beyond just muting the genes. They are exploring genetic knockouts.
Genetic knockouts, that sounds intense.
It is the cutting edge of genetic engineering. They are looking at creating poultry where specific genes, like the LDL receptor gene or the ApoE gene, are literally deleted from the bird's genome.
Wait, deleted entirely?
Yes. You are permanently altering the blueprint of the hen to force the production of low cholesterol eggs.
Wow. We're literally reprogramming the animal. And if gene editing wasn't sci-fi enough, we have to talk about the nanotechnology in the chicken coop. When I read this section of the review, I had to read it twice.
It is arguably one of the most fascinating and surprising frontiers in the entire review.
The review explicitly mentions feeding hens nanoparticles. We are talking about microscopic nanoscale particles of silver, gold, nanocurcumin, and chitosan.
Yep, nanoscale, gold, and silver.
Let's start with the obvious question. Why on earth are scientists feeding chickens gold and silver dust?
It's a great question. It's all about bioavailability and surface area. At the nanoscale, physical materials behave completely differently than they do at a macro level.
How so?
When you shrink silver or gold down to nanoparticles, their surface area increases exponentially relative to their volume. These nanoparticles are incorporated into the chicken feed, and when they enter the hen's gut, they act as extreme metabolic modulators.
Modulators, meaning what?
Well, what we can picture as microscopic sponges.
Sponges. How does a piece of nanogold act like a sponge?
Because of that massive surface area, they physically interact with and bind to cholesterol molecules right there in the digestive system.
Oh, wow.
They essentially trap the cholesterol so the hen's intestines simply cannot absorb it into the bloodstream. Or, depending on the material, they facilitate the breakdown of cholesterol into harmless byproducts before it ever reaches the liver's packaging plant.
It's absolutely wild. It's like we've gone from trying to fix a glitchy computer by just changing the brand of electricity it uses, hoping the garlic or mushrooms work, to actually going in and rewriting the source code with CRISPR or deploying microscopic nanobots straight into the hardware to clean up the mess.
That's a very accurate analogy. We are moving from blunt, indirect instruments to extreme microscopic precision.
So what does this all mean for you, the listener, and your morning scramble? We have these incredible tools now, from shiitake mushrooms and selenium memos all the way to gold nanobots and gene editing. But should we be doing this? What is the ultimate goal here?
If we connect this cutting-edge science to the bigger picture, we really have to look at the United Nations Sustainable Development Goals, specifically SDGs 2, 3, and 12.
Which are?
Zero hunger, good health and well-being, and responsible consumption and production.
Because, as we said at the start, eggs are a cheap, universally accessible, vital source of protein globally.
Exactly. We have a growing global population. We need to feed the world with high-quality protein, but we need to do it without exacerbating cardiovascular disease in metabolically vulnerable populations.
Those hyper-responders we talked about.
Right. Designer eggs fit perfectly into the overlap of those global goals. But the current debate in the scientific community is whether our methods are truly viable on a mass scale.
Right. Are diets enough? We saw that just throwing garlic or algae at the problem gives inconsistent results because the hen's body fights back.
Which is exactly why many top researchers argue that single-factor nutritional interventions are totally insufficient.
Okay, so what's the solution?
To truly create a sustainable mass-market designer egg that is consistently low in cholesterol, we must combine genetic omics with precision nutrition.
A two-pronged approach.
Exactly. We essentially need to breed a hen that is genetically optimized from birth to respond perfectly to specific, specialized feed additives.
But hold on. There has to be a biological limit here, right? If we use gene knockouts or nanobots to completely strip the cholesterol out of an egg, doesn't that fundamentally break the egg?
This raises a vital cautionary note, and the researchers are very clear about this. As we try to optimize the egg for humans, we have to remember why the cholesterol is in the egg in the first place.
Right.
That incredibly complex 24-hour armored truck delivery system we talked about earlier. It isn't running to make you a delicious breakfast. It's running to grow a baby chick.
Right. The yolk is the sole source of building blocks for a developing embryo.
Precisely. Cholesterol is absolutely essential for chick embryonic development. It is the core building block for their cell membranes. It's a mandatory precursor for their steroid hormones, their bile acids, their vitamin D.
So they need it to survive.
Absolutely. If scientists use aggressive gene knockouts or extreme nanotechnology to drop the cholesterol levels too low, the result is biologically unviable eggs. The chicks either won't hatch at all, or they'll have severe developmental issues and high post-hatch mortality.
So in our pursuit of a healthier human breakfast, we could accidentally engineer an egg that can't even sustain its own intended life.
Exactly. We have to be incredibly careful. The overarching goal isn't elimination, It's a very delicate balance.
Reducing it just enough.
Right. Reducing the cholesterol concentration just enough to significantly benefit human cardiovascular health, but keeping just enough in the yolk to maintain normal hen physiology and biological viability for the egg.
It is truly staggering when you step back and look at it all. A simple kitchen staple, something you can buy for a few dollars a dozen at any corner store, is at the absolute center of this massive multidisciplinary scientific collision.
It really is.
You have traditional agriculture, advanced genomics, and space-age nanotechnology all converging right there in your frying pan. Next time you crack an egg, you really should take a second to think about the complex estrogen-powered factory that built it.
There's so much going on in there.
Think about the VLDly armored trucks, the receptor keys, the genetic blueprint. It is a true biological marvel.
It really is a marvel. And as we map the genome and introduce these nanotechnologies, it leaves us with a profound philosophical dilemma to ponder.
Oh.
Yeah. If science can successfully engineer an animal to selectively withhold a naturally occurring, quote-unquote, flawed component like cholesterol from an egg, while somehow maintaining its perfect nutritional structure, what other natural flaws in our whole foods might we soon be able to edit out?
Wow.
And at what point of technological intervention, when we are deleting genes and feeding them gold nanoparticles, does a natural food stop being natural entirely?
When does that simple, comforting, smooth white stone stop being a natural vault and start being a manufactured pharmaceutical pill? It is definitely something to think about over your next omelet.